Welcome to 9040 EPL Aries Demo Kit Access Configuration. We'll be configuring the Aries-EPL drives. At the end of the session, you should be able to create a new project, set up the X and Y axis, select the correct motor files, and do a basic tune and test. We're going to create a new project, and our project name will be EPL Demo Kit. For our demo kit, we have an ACR9040. We need to select the ACR controller part number. The part number is located on the label on the side of the unit. In this case, we have a P3U0B0. Click Next. At this point, we can alias our controller. If we have multiple controllers, we'd want to name this something meaningful for our machine. We can click Finish. The first thing that you'll see is the project workspace. To be able to configure our processor, we need to connect to it. You can see from my connection here that my system does not have a serial port. I have one of the new laptops with USB ports only. I do have an Ethernet port, and I do have the ACR USB cable plugged in, and it's coming up as COM2 on my system. If I was to plug in a USB serial adapter, I could click on Find Ports, and it will go out and it will find that new serial adapter and make that available. For my Ethernet connection, this should contain the IP address of your ACR9040. By default, the address is 192.168.10.40 from the factory. In order to talk to this over the Ethernet, your laptop should be set to 192.168.10. something other than 40. In this case, I'm going to use the USB connection. So I click on the USB and say Connect. We can see at the bottom that I've connected successfully to my controller and that my project is loaded. I'm going to make a little more room for my configuration here. Once I've connected, I can minimize that. Next, select Configuration Wizard. Since the 9040 can support up to 16 EPL axes, we're going to need to tell it that we're only using 2 axes. By default, it sets the axes numbers to 0 and 1, giving them an alias of X and Y, which you can manually change. Your command output is EPLD 0 and 1, which corresponds to axis 0 and 1. The node IDs of 1 and 2 are set via the rotary switches on the front of the Aries drives. Master 0 is the master that the 2 nodes are assigned to if you want them to be interpolated or to do coordinated motion. If you wanted them to run independently, you could attach them to 2 different masters, say for 2 conveyors. But for our purposes, we want them both to be assigned to master 0. And go Next. To make sure that we're all wired up correctly, we want to check our EPL network. We can see that mine is operational and my network started, and it is exchanging data. We'll go Next. We have the CanOpen I/O on these demo kits. The default master node and information is correct for the attached unit. We can test it by starting the CanOpen network. We can see that it goes out and checks this network status, and it did successfully start. So everything is wired correctly, and I can move on. We'll go Next. In here, our master, we could give it a different name if we wanted to have multiple masters within our project. We specify the units, inches, millimeters, degrees, revolutions, etc. Since this is a rotary application, we're going to say revolutions. And for the acceleration ramp, we'll give it 100, velocity of 10, decel of 100. Stop ramp we'll leave set to 0, and we will not enable pure S-curve acceleration and deceleration. The pure S-curve acceleration and deceleration rounds off those edges for your sharp changes in direction or velocity. It's important to set these master motion defaults up. If you do not use the program to set these dynamically, it'll default back to these. In the case of an interpolated or dynamic motion or a coordinated motion, it's going to use these as its maximums. So it'll run at a maximum of this rate. We'll go next. To define the motor profile that we want to use, we're going to say create new configuration. We're going to select our motor part number from the label on the side of the motor, which is a series BE, 23 frame, single stack, D winding, J feedback, no additional heat sinking, and no, we do not want to edit the mechanical and electrical parameters. If you were using a custom motor, you could come in here and modify things like torque, voltages, a lot of different things that you can do to make other drives work with it. But our motor file has all that information in it. So we're going to go next. Configuring the fault outputs. We do not want a fault when the drive disables. We want to be able to disable the drive without setting a fault in the controller. And we do not want to disable our motor thermal sensor. So we're going to go next. Then we're going to download the configuration to our Aries drive. It'll open up an EPL network session to the drive. Download the configuration. That includes the motor file that we just set up. Then we'll go next. Our position feedback is going to be EPL feedback, and the source will be EPLD0 for axis 0. And next, our transmission type, we do not have any other transmission on this. If this was attached to a rotary table or some other mechanics, we could tell it what it's attached to. Or if we had a gear reducer, we can give it the reducer type and how many revolutions equal revolutions out. We'll say next. We're not using hardware limits on this demo kit. If we had a linear system, we'd have our positive and negative hardware limits. And here's where we would set up the I/O that those limits would be attached to. Maximum position error. Since this is a rotary system, positive and negative position is actually one full revolution. If this was in millimeters, we'd want to set something greater than 1. Click Next. From this screen, we see the default servo gains. The default servo gains, proportional and derivative, are set somewhat soft. We're going to go ahead and enable our drive. We see that our drive is enabled and drive is not faulted. We're going to see what kind of response we get from our motor drive combination. We're going to do a positive step move. What the positive step move does is it does a little bit of motion and compares the feedback motion to the commanded motion. We can see that we had a little overshoot, undershoot, and some ringing. So that's fairly soft, and if you would grab a hold of the motor, you can turn the shaft and you can see it's kind of spongy. We're going to adjust the proportional and the derivative gain. You want to make small changes to the proportional and derivative, and you want to make the changes to both at the same time. Applying a lot of proportional gain will give you quicker response, but it'll also cause the motor to run away or go unstable unless you give it enough derivative to kind of damp out that action. So we're going to do a small change here. We're going to just use the up arrow to run this up to the last 2 digits of 20. And let's just add a couple of points to our derivative gain. And we'll do our positive step move again. And we can see after this runs that our overshoot and undershoot are reduced somewhat, and the ringing is somewhat reduced, but it's still not really good. So what we're going to do is we're going to bump it up just a little more. Remember, small changes have big effects. So we'll just bump that up to a last digit of 5 for both. We'll do a positive step move again. And the result of that is we have a little overshoot, a little undershoot, and then very little ringing, and it's fairly stable from there. So that's a good initial tune. That'll keep our motor from running away, and we're not overstressing it. It's no danger of going unstable. So we'll go next. From here, if we had hardware limits, we can test these for commissioning. Any software limits, we can see that our commanded position and actual position are very close and well within our parameters. Position error, our max position is not exceeded. I want to go ahead and try to jog this motor, so I'm going to give it a little bit of update to its settings here. The acceleration, deceleration, we want to go to 100. Velocity of 10. We'll say OK. It says it's ready to jog. I'm going to jog negative. And you can see from the commanded position and the actual position that my motor is actually moving. And it is jogging. I'm going to go next. So now I've completed the x-axis. I need to set up my y-axis. Again, the drive is an Aries-EPL. We'll do create new configuration. It's a BE 23 frame, single stack, D-winding, J feedback. No additional heatsink, and we're not editing, so we go next. We're not setting either of these, so we'll go next. We'll download our configuration. Okay, it's finishing its download. So we successfully downloaded our configuration to the y-axis. The EPL feedback for axis 1 is EPL D1. So we go next. No transmission type, no reducers, so we go next. No hardware limits, we go next. And we're going to test this. We know from experience now that a good starting point would probably be 25 as the last 2 digits and a 15 as the last digit. And the only reason I can do this is because it was actually the exact same drive and motor combination. And even within those combinations, you'll have a slight variation. But for as loosely as these were tuned, this should be a good starting point for us. So I'm going to now enable the drive and have it do a positive step move. And what we see from this step move is very similar to what we saw in our x-axis. So this is a good starting point. So we're just going to go next. Again, we can go in and make sure of what our settings are here. We can jog the motor and make sure that we can do motion. So my motor is jogging. Looks good. I'm going to go next. By default, an ACR9040 does not have any memory settings. One that's never been configured when you come in would look something like this. 20,000 bytes for the program 0 and nothing else defined. What I want though is about 250,000 in program 0. Program 0 is assigned to master 0. So the program for motion that we create for our demo here is going to be in program 0. Programs 0 through 7 are motion programs. So anything that has to do with creating motion has to be in programs 0 through 7. And they all have their own time slice. The programs 8 through 15 all share one of those 1 millisecond time slices. So whereas the program 0 through 7 have their own 1 millisecond time slice, program 8 through 15 all share one of those. Now we do have a non-motion program for an EPL and CANopen system. We need to initialize our EPL network on boot up. So for program 8, let's go ahead and just put in 50,000 for the starting memory for that. By default, you have 4,096 global variables and 20 defines. If you're running low on memory, you can reduce these, but by default, we can just leave those set to where they are. We'll go next. If we made any gross configuration errors, let's say I told it that I wanted it to use hardware limits, then didn't give it any addresses to use for those limits, it would tell us here, and we could go back and fix that. Since we're not getting any errors, we're going to go ahead and say finish. It's going to generate our configuration file and then let us download our configuration and our defines. We're going to say OK. So this is going to update the controller with the configuration we just created for our EPL Aries drives. Downloads any programs. Now on the download summary, we can see that everything downloaded, and under this note, only memory allocated programs have been downloaded. If we had created programs in, say, program 1 and 3, those would not have downloaded because we didn't define any memory for them. So only memory allocated programs have been downloaded. We'll say OK. And at this point, we've successfully done the basic configuration for our ACR9040 demo kit. This is the end of this session. Key points to remember are to verify the Aries and ACR model numbers from the side labels. Coordinated axes of motion must be assigned to the same master. When defining the motors, select Create New Configuration before making the drop-down selections. When tuning, small changes have big effects, so take it slow.